Assalamu alaikum.
Walaikum assalam.
End out from last class.
No, sir.
Okay. So in last class we have just completed this thermal properties of matter. So next we have to start with new chapter, that is thermodynamics. Next is thermodynamics. It consists of two different words, therm and dynamics. Therm means heat and dynamics flow. So we can say the study of flow of heat, or the responsible factor to flow heat from one point to another. And next is conversion of heat energy into mechanical energy or some other form of energy. So in this entire chapter, we mainly define only these two different parts. First, flow of heat, and second, conversion of heat into some useful other energy, just like mechanical energy. So we define thermodynamics as the study of flow of heat and conversion into mechanical energy or other useful energy. So to define this thermodynamics, let me define you some basic concept behind it. First is thermodynamical variable. All the different physical quantity which may define condition of gas at any instant, just like number of moles, pressure, volume, temperature, and so on. So these different physical quantity are termed as thermodynamical variable. So you can say the quantity on which condition of gas may depends upon. Now to define relationship, or which states simply condition of gas at any instant, we may rearrange these different thermodynamical variable in a fixed manner or fixed equation, which is called equation of state. Hamza, any doubt?
No, sir.
Okay. So next is equation of state. It's simply an equation between thermodynamical variable which defines process or condition of gas at any instant. The relation between thermodynamical variable, just as number of moles, pressure, volume, temperature, which defines process or condition of gas at any instant. So in general, first, Pv to the power x equals to constant. Second, P raised to 1 by x, V is equals to constant. And ideal gas equation, PV is equals to nRT. First, write it down to this part. Hamza, done?
Sir, the last part.
Okay.
Done, sir.
Khalid, any doubt?
No, sir.
Okay. Now, related to this part, for all different process, we have to calculate molar specific heat constant, which I have already defined in last chapter. It is the amount of heat required to raise temperature of gas at a given condition by 1 degree centigrade. So it will be dq equals to n times c dt. So c equals to dq divided by number of moles times dt. But in general, c equals to r by gamma minus 1 minus r by x minus 1. So on knowing the value of x, you'll be able to calculate c related to that process. In this part, r is universal gas constant, which is equals to 8.314, or you may use 25/3 joule per mole per Kelvin. Now, in this part, next is gamma. So to define this gamma, let me define you another term. Degree of freedom. So what do you mean by degree of freedom? To define this, let me give you some example. First, suppose you have any monatomic particle like helium, argon. So if you have to calculate energy associated with this part, you will say it may move translationally along x-axis, y-axis, or z-axis. It means this monoatomic particle will have tendency to move along these three different coordinate axes, or you'll say it will have translational motion, due to which it may contain translational kinetic energy. So in this part, it having three different ways of translational kinetic energy. So number of ways in which a particle may contain energy is called its degree of freedom. So for this monoatomic particle, it will be 3. Similarly, suppose you have diatomic particle. So it will move along this axis, or this axis, X, Y, and Z. Means it will have 3 translational motion. So this diatomic particle will move along this axis, or this axis due to its translational motion. And we may define its rotational motion also. Suppose this is any bond and particle attached at its endpoint behaving as diatomic particle. So it may move along this axis, X, this axis, Y, or this axis, Z. It means it will have 3 translational energy. It may rotate along this axis, that is along Z axis. It may rotate along this axis, X axis, but there will be no rotation possible along Y axis, since along Y axis it will behave like point object for which there will be no possible rotation with it. Is it clear?
Yes, sir.
So we may define this diatomic particle will have rotation along this axis, along this axis. There will be no rotation along y-axis. So in total, it will have 3 translational motion and 2 rotational motion, 5 different ways of energy containing. Next, let's say in case of water molecule, which is bent shape like this. So it will have translational motion along this axis, along this axis, and along this axis, X, Y, and Z. Translational motion, and translational motion. It may rotate along this axis, also along this axis, and there will be also rotation possible along this axis also. So it will have 3 translational and 3 rotational motion. So we can say degree of freedom is all different ways or coordinate in which a gaseous particle or molecule may contain energy is called degree of freedom. Hiba, is it clear?
Yes, sir.
So it is the number of ways or coordinate in which particle may contain energy is called degree of freedom. So in first part, for monoatomic, just like helium, argon, number of degree of freedom is 3, and all are due to its translational motion. Second, in case of diatomic, such as hydrogen, nitrogen, oxygen, and so on, it having 3 translational energy and 2 rotational energy. So in total, it will have 5 degree of freedom in just one molecule. In triatomic, I'm just considering H2O molecule. This will be not valid in case of CO2, since CO2 exists as linear, so it will have just 5 degree of freedom, just like diatomic particle. So number of degree of freedom for this will be 3 translational and 3 rotational, that is total 6. Salman, any doubt?
No, sir.
Okay, just write it down. Hamza, down.
Sir, drawing the last one.
Okay.
Done, sir.
Okay. So next, related to this degree of freedom, you will be asked on what factor this degree of freedom may depend upon. So let me define you. In first part, we have just monatomic. So it is having only 3 degrees of freedom. But in case of diatomic, number of degree of freedom is 5, which is more as compared to monatomic. But for triatomic, having bent shape, it is 6. It means it may depend upon number of particle or atom in that molecule. Next, it may depend upon their geometry. If it is linear, it will be always 5. It is bent shape, it will be always 6. And if it is point object, it will be always 3. It means it will depend upon their geometry or shape. And next, further, it will depend upon temperature. Is it clear?
Yes, sir.
So on what factor this degree of freedom may depend upon? So you will be asked factors affecting degree of freedom. So first is number of atoms in one molecule. Second, their geometry or shape. And third, temperature. So you'll be asked how degree of freedom of particle may depend upon temperature. So let me define you this part. At low temperature, particle may get attached with some other one having stronger bond in between them. But if you increase the temperature of that particular molecule, bond gets slightly weakened. So it will tend to vibrate also in between them. It means on increasing temperature, bond gets weakened. So additionally, this degree of freedom may contain vibrational part also. Hence, degree of freedom increases with the rise in temperature. Suppose you have diatomic particle having bond in between them at low temperature like this. So if you increase the temperature, so on increasing temperature will tend to decrease in strength of bond. So at that time, it will tend to behave like a spring. So they will start vibrating also, in addition with these two different translational and rotational motion. Hamza, is it clear?
Yes, sir.
So degree of freedom increases with rise in temperature, except for monatomic gas. If temperature increases, bond get weakened. So vibrational energy of molecule increases. Hence, degree of freedom increases. Khalid, any doubt?
No, sir.
Next, what do you mean by gamma? Gamma is called specific gas ratio, which is equals to Cp divided by Cv. I will define you later what do you mean by Cp and Cv. C is called molar specific constant and P subscript part define its process. So Cp is molar specific heat at constant pressure and Cv is molar specific heat at constant volume, which is equals to 1 plus 2 by F, where F is number of degree of freedom. So if you put the number of degree of freedom related to monoatomic, diatomic, triatomic, so gamma for monoatomic will be 1 plus 2 by 3. That will be 5 by 3, 1.67. Gamma for diatomic, 1 plus 2 by f, f is 5, so it will be 7 by 5, that is 1.4. And gamma for triatomic, 1 plus 2 by f, f is 6, so it will be just 4 by 3, that is 1.33. Now just compare these different gamma. You'll say it is maximum for monoatomic and minimum for triatomic. So gamma monoatomic is maximum, then diatomic, and then triatomic. And these all should be greater than 1, but always less than 2. I'm just considering or calculating degree of freedom of gamma just for one particle or just one molecule. If you have to calculate for n number of particles, just multiply it by n to get total number of degree of freedom. Salman, is it clear?
Yes, sir. Okay.
Okay, just write it down. Have you all done?
Sir, can you explain this one again? Like, how did you get 5 and 7 and 4? Like, then,
Okay, just 1 minute. According to what we got for degree of freedom, just for monoatomic, we have degree of freedom is 3. For diatomic, in total, we have 5. And for triatomic, we have 6. On putting these different values in this expression, 1 plus 2 by f, f is 3 for monoatomic. So 3 plus 2, 5 by 3. So it will be for monoatomic. If you divide this fraction, you'll get this part. For diatomic, where number of degree of freedom is 5, so 5 plus 2, 7 by 5, that will be 1 by 1.4. And similar triatomic. Hamza, is it clear? I'll
yes,
just
sir.
put the value of f in this part and take and solve this fraction. Okay. Next is concept of gas about real gas and ideal gas. So next is real gas and ideal gas. Hamza, do you know these two terms? What do you mean by real gas or ideal gas? Khalid,
Yes, sir.
what do you mean by real gas and ideal gas?
Ideal gas means it like follows the laws, the Avogadro law, another law. I forgot the name of laws.
Okay, okay.
And the
And then,
real gas is the opposite of ideal gas. It does not
okay,
follow the laws.
okay, okay. Let me define you its actual meaning. Suppose you have a particle, this point and this point. If there is interaction between particles, so due to interaction, it will have some potential energy due to their attractive or repulsive force in between them. So if there is interaction between particle of gas, then it will have some potential energy due to interaction. And since this interaction is always attractive, so potential energy will be negative. Next, it must have some temperature, so due to which it will have some thermal kinetic energy due to temperature. So if you add these two energy, so total energy related to gas is called internal energy, represented by U, which is equals to kinetic energy plus potential energy. Now, in case of ideal gas, we assume if there is no interaction between particles, it means this particle will exist independently and there will be no interaction in between them. If there is no no interaction between particle of gas, it means potential energy will be zero. That will have only kinetic energy due to temperature. So total energy will be just equals to kinetic energy or due to temperature. This gas is called ideal gas. Is it clear? So in general, you will say a gas in which if there is interaction between particles, due to which it will have some potential energy due to interaction, it will be termed as a real gas. And if there is no interaction between particles, so there will be no potential energy of interaction, then it will have only internal energy due to its temperature. It is termed as ideal gas. So next concept is on what factor real gas will tend to behave as ideal gas, or on what factor it will tend to obey different laws like Avogadro's law, Dalton's law, or something other. So let me define you. In real gas, we have interaction. So on what factor this interaction may depend upon. Suppose you have any vessel with a piston containing just 5 particles, I'm just assuming. So if you compress this particular piston slightly downward, so will the separation between these particles increases or decreases?
Increase.
Good. And if you extend this particular piston outward, so separation between particle increases or decreases?
Increase.
Good. Now, this interaction or attractive force between any two particles will be inversely proportional to their distance, like electromagnetic force, like gravitational force. So if you increase the separation between particle by anyhow, interaction between particle get decreases. So in this part, on moving this piston slightly outward, we are just decreasing pressure of this particular system. So if you decrease the pressure, separation between particle increases, hence potential energy in between them decreases. Is it clear? Hamza, any doubt?
Yes, sir. No, sir, no doubt.
Next, if you increase the temperature of this particular system, then on increasing temperature, particle will tend to move randomly in different direction. So in that case also, there will be least interaction in between particle. So we have to simply decrease the interaction of particles so that it will tend to behave as ideal gas. So from this part, we may conclude at low temperature, low pressure and high temperature, there will be least interaction between particles. Hence, the real gas will tend to behave as ideal gas. So from this part, we can say at low pressure and high temperature, real gas will tend to behave as ideal gas. Hiba, any doubt?
No, sir, no doubt.
Okay. Just write it down. Salman, written.
Yes, sir.
Okay, next is What do you mean by system? Surrounding. Suppose we have any vessel piston enclosing any ideal gas. So this gas is under observation, for which we have to calculate different physical parameters such as pressure, volume, temperature at different state. So this gas is called system. Surrounding is all the influencing factor from outside which may influence this system by any means is called surrounding. And these two terms combinedly called universe. So we can say universe may divide into two parts. First is system and the second one is surrounding. So system is the gas enclosed in vessel which is under observation is called system, and surrounding is all the influencing factor from outside which may affect system in any way is called surrounding. Hamza, any doubt?
No, sir.
So on the basis of interaction between system and surrounding, we may divide this system into three different types. First is called open system. Second is called closed. And third is isolated. So open system, a system which may allow exchange of matter and energy between system and surrounding, it is termed as open system, which allow exchange of energy and matter in between system and surrounding. That is called open system. Closed system, which allow exchange of energy only. There will be no exchange of matter, is called closed system. In isolated system, there will be no exchange of either energy or matter. It means no exchange of energy and matter can take place. Salman, any doubt?
No, sir.
Okay, just write it down. Hamza, done?
Yes, sir, done.
Okay. This is the introductory part of this thermodynamics. We have to use all these terms in all upcoming different topic. So first we start with thermodynamical law. So first is Zeroth Law. Since it is defined after first law and there is no any natural number before 1, so that it is named zeroth to assign previous to first law. It defines concept of temperature. Suppose we have an enclosed vessel which restricts any exchange of heat between system and surrounding. So this is called adiabatic wall, which restricts flow of heat through it. Next, there is another wall at this point, which is called diathermal wall, which allows exchange of heat through it. Allow exchange of heat. So we have three different systems. This is C, A, and B. All are initially at different temperature. So only exchange of heat can take place through this diathermal wall. So we can say there will be exchange of energy or heat between A and C along this path. Similarly, there will be exchange of heat along this path between B and C. So exchange of heat between any two thermodynamical systems will be due to its temperature difference from higher temperature to lower temperature till they acquire thermal equilibrium. Is it clear?
Yes, sir.
So from this part, we can say we have two thermodynamical systems, A and B. Individually is in thermal equilibrium with third system, C. Then on attaining thermal equilibrium, temperature of A becomes C or get equivalent to C. Similarly, temperature of B get equivalent to C. Hence, A and B must be in equilibrium with each other. So if you remove the wall of this A and B junction, there will be no further flow of heat between A and B, since A and B is in thermal equilibrium at that time. So from this entire segment, we may conclude temperature is the physical quantity which is responsible for flow of heat between any two thermodynamical system till they acquire equilibrium. Is it clear? If two thermodynamical system is individually in thermal equilibrium with third system, then they must be in equilibrium with one another. It means temperature of A becomes equals to C, temperature of B equivalent to C, then A must equivalent to B. So we can say temperature is the physical quantity which is responsible for exchange of heat between any two thermodynamical system. Temperature is the physical quantity responsible exchange of heat between two thermodynamical system. That's why Zeroth Law is called, or simply it is responsible to define concept of temperature. Hiba, any doubt?
No, sir.
Just write it down. Hamza, done?
Yes, sir, done.
Okay. Next is first law of thermodynamics, which is based on conservation of energy. It means energy neither be created nor be destroyed, only it transformed from one form to another. Suppose you have gas enclosed in a vessel. If you supply heat to this particular system, or if you eject out heat from this particular system, it may be utilized in two different processes. First, if you have supplied heat to this particular system, it will be utilized in changing its internal energy and doing work on the piston to expand it from this point to some new point this. Similarly, if you eject heat from this system, it may be due to compression of piston from this point to this and to change its terminal energy du. So according to this, we may define state energy neither be created nor destroyed, only it transformed from one form to another. So according to this part, we may define the amount of heat supplied or ejected out from this particular system may be utilized in two different processes. First, to change its external energy, and second, to do some useful work. So you may define according to this concept as the amount of heat ejected or supplied to system is utilized in changing internal energy as well as doing work. Hamza, any doubt?
No, sir.
So we may write according to this conservation, dq equals to du plus dw, where dq is heat supplied or ejected, du is change in internal energy, and dw is work done. Just write it down, then I'm defining with these three different terms individually. Hamza, done?
Yes, sir.
Okay. Now, related to these different three quantity, dq, heat, internal energy, and work, we may divide into two parts according to their property. First is state function. In chapter 6, I defined you conservative force and non-conservative force, in which conservative force means force for which work done is path independent, it just depends upon initial and final point, is termed as conservative force. Or for non-conservative force, the force for which work is path dependent are called non-conservative force. Similarly, state function is the physical quantity which may depend only on initial and final point of gas. It will be independent of path followed by the gas, just like conservative nature of force. Then it is called state function. Is it clear? Khalid,
Yes,
any
sir.
doubt? So state function we have first is internal energy or entropy. So state function is the quantity which depends upon initial and final point. It is independent of path followed by gas. That is called state function. So in this, first is internal energy. So du equals to number of moles into Cv into dt, where Cv is called molar specific heat at constant volume. So it will be equals to N times F divided by 2 R into dt, which is also equals to N R times dt divided by gamma minus 1. So it will be equals to B initial minus P final V final divided by gamma minus 1. So you may use these different formula to find internal energy. Now, according to process, this is pressure versus volume. We have three different paths, one along this way, and along this way. Same initial and same final for all these three different paths. Let's say this is path first, path second, and path third. So you'll be asked, what will be the relation between change in external energy along these three different paths? So you will say, since initial and final point for all these three different paths is same, and change in internal energy depends upon only on initial and final point, So these three must equal to each other. Is it clear?
Yes, sir.
In second part, suppose this is pressure versus volume, which is for any cyclic path. It means initial point and final point will be same. So change in internal energy, just like displacement for closed path will be zero. So change in internal energy along closed path will be zero. So just remember, for cyclic process for whole complete path, initial and final point both will be at same. So change in internal energy will be zero. Khalid, any doubt?
No, sir.
Okay, just write it down. One more thing about its sign convention. If temperature increases, change in internal energy will be taken as positive. And if temperature of system decreases, change in internal energy will be taken as negative. Just use the sign convention. Hamza, done?
Yes, sir. Done.
Okay. Next is path function. Just like non-conservative force, the quantity which may depend upon path followed by gas are called path function, such as heat and work. The quantity which depends upon path followed by gas. It will be independent of initial and final point. That is called path function. So first is heat. For any different formula or any different process, we may use dq equals to nc dt, where C will be molar specific heat related to that process, where C is molar specific heat, constant related to that thermodynamical process. Like we have different process like isobaric, isoporic, isothermal, adiabatic. For all different process, it will have different value, and related to which we may define different heat. Sign convention related to this part is if heat supplied to system, then it will be taken as positive. If heat being ejected out,
No, sir.
okay, just write it down. Hamza, done?
Yes, sir, done.
Okay. The next part is calculation of work done, which is the most important for this entire chapter. So next is work done. Work done is equals to force times displacement. We may write force as pressure into area times displacement. Area into displacement or area into length is called volume. So it will be P multiplied by dV. Integration. This particular quantity in terms of graph will also equals to area under pressure volume graph. So work done is simply P dV integration or simply area under pressure volume graph. Now related to this part, suppose there is a vessel and a piston attached enclosing any gas. This is pressure versus volume. Suppose particle of this gas is applying some force on it to stretch it or to expand it from this point to some new point, this. It means volume of gas will increase from initial level to some final level. So let's say this is initial point A. On extending, pressure will change and volume will change along this way. So initial volume is VI, final volume is VF. If you extend this particular arrow, it will go along this way and may act as clockwise notation. So area under this particular curve between pressure and volume will define your work done. And since it is in clockwise direction, so let me define a different part related to this. First, volume of final is greater than volume initial. So change in volume will be positive. It means work done will be positive. In this part, volume is increasing. It means expansion of gas. Next, particle of gas is doing work on piston to expand it. So we can say work is done by the system. That is system of particle. And related to this, graph is in clockwise direction. So we may define these 5 different terms related to this process. Hamza, is it clear?
Yes, sir.
Similarly, just opposite of it, let's say this is any vessel. Piston is initially at this point, enclosing any idle gas. So from outside, if pressure is applied on this piston to compress it, to change its volume, finally to this point from some initial larger volume. So pressure versus volume variation for this process will be like this. From some point A along this path to reach at this point B. So if you draw or extend this particular direction of arrow, you will get a curve in anti-clockwise direction like this. So area under this graph will define you work done for this process. So this is V initial and V final. So in first part, V final is smaller as compared to V initial. So change in volume in this part will be negative and work done will be negative. Second, gas is compressing. So compression of gas. Next, work is done by any external agency on this particular piston to compress it down. So work is done on the system. And next, in this part, graph obtained is in anti-clockwise direction. So graph is in anti-clockwise direction. Khalid, any doubt?
No, sir.
Okay, so just remember these different properties related to the work done. Just write it down. Hamza, done?
So writing the second one.
Okay, okay.
Done, sir.
Find first work done, second heat, and third change in internal energy. if we have this is pressure versus volume. One of the coordinate, this is V0, and this is 3 times V0. This is P0, and this is 2P0. Along this way. Try to find using the above concept related to these different terms. For any curve in physics, if you have to calculate area, you just use pi r1 into r2. R1 will be along x coordinate and R2 will be along y coordinate. So just use this method or formula to find area under this particular curve. And try to find these 3 different terms. Just use this value and put in the above part, you'll get work done. So first, work done is area under PV curve. Area is pi R1 into R2. R1 is V0 and R2 is P0 divided by 2. So it will be pi P0 V0 divided by 2. What would be the sign of this particular work done? Positive or negative? Hamza?
The positive.
Why? just look at direction of rotation or notion of direction of this particular curve. Is it in clockwise or anti-clockwise?
The clockwise.
Good. That's why work done will be positive. Salman, any doubt?
No, sir.
What will be change in internal energy for this particular path? On what factor change in internal energy may depend upon?
The 0.
Good. Since this particular path is closed path, and for closed path, initial and final point will be same, so change in internal energy will be 0. It means change in internal energy for any closed path is 0. So according to first law, we may write dq equals to du plus dw. Since du is 0, so amount of work done in this process will be equivalent to heat. So dq equals to dw, which is equals to plus pi p naught v naught divided by 2. And since this heat is coming out to be positive, it means it must be supplied to the system. Khalid, is it clear?
Yes, sir.
Iba, any doubt?
No, sir.
Okay, just write it down. Salman, done?
Yes, sir.
Okay. Now suppose from A to B and then C. Gas is going first along this way, then along this way. A to D and then to C. So for both these two parts, we have same initial and final point. So states for path A, B, C, heat supplied to system is 100 joule and work done on the system is 20 joule. And for ADC, heat work done by the system is 30 joule. Find heat supplied during this. Let me give you a hint how to solve this part. In both process, we have same initial and same final point. So which of the quantity, heat, internal energy, or work done will be same in both different paths? Iba? Which quantity will be same along both different two process? Hamza? We have same initial and final point for both these two processes. So the quantity which depends only on initial and final point, independent of path followed by the gas.
The work done.
It should be internal energy, okay?
Okay, sir.
Since we have same initial A and same final C, so for both these two paths, we'll have same internal energy. So according to first law, dq equals to du plus dw. Since initial and final point is same, so du is equals to dq minus dw. So it means for same initial and final point, change in internal energy along path 1 should be equals to change in internal energy along part 2. So internal energy equals to dq1 minus dw1 equals to dq2 minus dw2. We have to calculate dq along second path. Now, in the question we have given heat supplied to the system is 100 joule, for which work done on the system is 20 joule. In second part, we have work done by the system is 30 joule. So using sign convention, we may write first heat supplied to the system. It will be positive or negative? Hamza?
The positive.
Good. So dq1 will be positive, 100 joule. Work is done on the system. So it will be positive or negative? Work is done on the system. Negative.
Negative.
Good. So minus 20. dq2, we have to calculate work is done by the system in the second process. So it will be positive. Now just simplify it. 100 plus 20, it will be 120 equals to dq2 minus 30. So dq2 equals to 120 plus 30, it will be 150 joule. So this will be a final answer. Khalid, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Hamza, done?
Yes, sir. Done.
Okay, any doubt up to this part in this entire chapter?
Not yet, sir.
No, sir.
Okay, just revise this whole concept. We'll continue next class, the different process related to this part. Okay, that's all for today. Take care. Allah Hafiz.
Thank you, sir.
Okay,
Allah
sir.
Hafiz.
Allah Hafiz.
Yeah.